Hey, hi everyone. Sorry to get going a little bit after the hour. This is Dan Barry from the NOAA Climate Program Office, and thanks everyone for joining today. So this is actually not a typical MAPP webinar for those of you who tend to attend our webinars. This is actually a call of the Climate Prediction Task Force, which is a task force that our research program formed back in the fall of 2012, and the membership of the task force is drawn from individuals that we fund who are doing work in the area of prediction and predictability on various timescales, largely subseasonal to interannual timescales. And they have monthly phone calls and decided for this month's phone call to focus on the NAO, which is a hot topic for prediction and predictability research, exploiting it for improvements in prediction skill. And so we decided to open this up as a full webinar with the thought that the broader community would probably be interested. So we have a mixture of individuals from the task force as well as individuals from the broader community on the line today. The task force is led by Ben Kurtman, and it's co-led by Arun Kumar, Matt Newman, and Tony Barnston. And just one more note before I hand it off to Ben, who's going to MC this webinar today. We have two speakers, and they'll each give talks that are about 20 minutes in length, and then we'll have 5 minutes for questions after each of the speakers, and then hopefully 5 to 10 minutes for discussion at the end, and we'll try to wrap this up at noon Eastern time. Both of our speakers, you may have noticed, are in England, so we're going to try to wrap it up at 5 so they can go on with their evenings. So in order to do questions, we're going to try something new for a webinar, which is to do the raise hand feature, and it's really simple. All you have to do is go into the participant list, which if you're on a Mac, you can go to the top of the screen. There should be a You're Viewing the Climate Program Office Host desktop bar. If you hover over that, there will be a participants list, and then at the bottom of the participants list, there's a hand logo, which you click, and then we'll be able to see that you have a question. I'll unmute your line, and then you can ask your question. And don't forget to put your hand down unless you have another question. If you're on a PC, you can find the participant list from the menu bars on the top of the screen, or you may have panels on the right-hand side of your screen, and you can draw up the participant list there. Okay, so without further ado, Ben, you on the line?
Yeah, I'm here.
Okay, Ben, take it away.
Sure. First thing I want to do is thank Adam and Tim for agreeing to do this. And I just want to say one or two sentences of motivation for this focused effort on the NAO. And that's based actually on feedback from NOAA operational forecasters. We had, at the Climate Prediction Task Force, we had John Gottschalk, who leads that group, give a presentation. At one point I asked John, or someone asked John, what's the biggest thing you need in order to improve forecasts at this moment in time? And his answer was very quick. He said he needs a better NAO forecast. And so this has become an issue of discovery for the Climate Prediction Task Force. We want to understand what's limiting us to predict the NAO, where we stand in predicting the NAO, and Adam and Tim have graciously agreed to get us up to date and identify what the major issues are. So with that, I would like to turn this over to Adam first and let him begin. So Adam.
Yeah, and Adam, this is Dan. If you could just share your desktop so we can see your screen, then we'll be ready to go.
Oh, is that not working yet? Hang on. How's that?
There we go.
Yep. Yeah, looks good.
Okay, thanks, Ben. So I'll speak for no more than 20 minutes. What I'm going to do is go through some of what we think are quite exciting results coming out of our latest seasonal prediction system, GLOSSy 5, Global Seasonal Forecast System 5. What we find in there, as you'll see, is well, stronger than a hint, but exciting evidence that there may be significantly higher levels of predictability for the NAO than we previously thought. And as the title screen shows you, that, of course, will lead to skillful prediction of European and North American winter climate. So the system that I'm talking about is this GLOSSy 5 system. It's now running operationally at the Met Office. It's based on our climate model had Gem 3. H stands for high resolution. And by high resolution, we mean N216. Now, the N216 is code for 216 waves around a latitude circle, and that's code for 432 grid points. So the resolution of this model in the atmosphere is about half a degree, 3/4 of a degree in the horizontal, and in the vertical we have 85 levels going up to the mesopause. So we have a good representation of the stratosphere and mesosphere. And then the other high-resolution component is the ocean, where we've pushed the boat out a little bit and gone to 1/4 of a degree. So that's 4 times higher than our previous system, which was at 1 degree. So the system is expensive, but we had good reasons to put those things in, and hopefully you'll agree that the results are worth it. In terms of initialization, the only thing to note really is that we initialize interactive sea ice, which I guess is not so common in some systems, but otherwise fairly standard approach. It's an uncoupled assimilation, so the atmosphere and the ocean are assimilated separately and then bolted together. And all the results I'm going to show you in the next 1/4 of an hour or so are winter hindcasts. So we only find a jump in skill in the winter, not the summer. And everything is based on 24 members starting around the 1st of November. And by that I mean between the 25th of October and the 9th of November, because this system, like the CFS, is a lagged initialization. So 24 members per winter, and I'm going to show you results from 20 winters. And much of what I'm going to show you was published in GRL in this paper here, Scaife et al., earlier this year. So this is kind of the headline result. What I'm showing you now is the 20-year hindcast from early November. And what you've got there is 1993 on the left, 2011-12 on the right. The black line is the observed NAO, and here we use the grid point sea level pressure index, so the kind of most basic measure, the surface measure of the NAO. And then the orange line is the ensemble mean, and each orange spot is an ensemble member. So you can see immediately that the ensemble mean follows to some degree the observations. The degree to which that is true is represented by the correlation score, which is 0.62 for this 20-year period. You can see prominent positive years like 2000 and 2011-12 are successfully reproduced, and then there are also negative deviations in the very cold negative NAO years like 2009-10, 2010-11. If you take that correlation, allowing for the very small autocorrelation from year to year, then the result is still significant at the 98% level. So we're pretty confident that there is skill here for the NAO. I can say that we've run this same hindcast more than once with an iteration to the dynamical core, and we get very similar results. So it is not a fluke, it is reproducible. Another interesting factor, and there are many interesting things that are popping out now as we look more deeply into the system, is first of all we get very similar results for the Arctic oscillation. So the correlation score is within a few hundredths, I think it's 0.6 or something for the AO. And interestingly, in the September, October, November period, we get a very similar result for the southern annular mode. So there is a symmetry here between the two hemispheres, and we have correlation score of about 0.65 for the SAM in the SON season. So I think that's kind of interesting because perhaps it suggests that either some of the skill is coming from the tropics or possibly the stratosphere, but we'll go back into that in a moment. For those that are interested in the PNA, then the PNA ensemble mean correlation with the observations is 0.92 over this 20-year period in this system. As you know, the NAO is related to blocking, so I thought I'd just show you an example of the skill in blocking. So these panels on the left here, the grey shaded ones, show you the climatological frequency in blocking. In the bottom panel, the bottom square, that's the ERA reanalysis data. In the top one, it's the Glossy 5 hindcast. And this is just the climatological frequency of blocking, which I hope you'll agree pretty nicely reproduces the observed frequency. And there isn't really much sign of a deficit in blocking in these hindcasts, which is interesting, given that many climate models show that feature. And then on the right, we have the actual skill in blocking. And you can see patches of skill over North America, Northwest Europe, North Pacific, in the places you might expect where there is intense blocking in the winter season. So there is some skill in the blocking frequency from year to year. The numbers there are quite respectable. They're up to, again, around 0.6. So what does this mean in terms of surface climate prediction? Well, if you look at the raw data coming out of the model, we look at things that long-range forecasters might be interested in, things like storminess, temperature, wind speed. Then on the left, the A, C, and E panels show you the correlation between the raw data that comes out in the ensemble and the observed frequency of storminess. So what we've done here is we've taken the 10th percentile of the daily sea level pressure as indicative of a storm. So anything at the 10th percentile or below is classed as a storm, and we count the number of those events at each grid point, and then that gives you a number of storms per winter at each grid point, and we do that for all the ensemble members, tot up those numbers, and the interannual correlation is what's shown here. So red is obviously high correlation. The sort of hatching, the shading thing shows the statistical significance. I think it's at the 95th percent. I can't remember exactly. It's either 90 or 95%. So what you see is over North America and over on the other side of the Atlantic, over Europe and North Africa, you can see large swathes where the storminess, the temperature, and indeed the wind speed are all showing skill now, particularly in Northwest Europe, for example, for the wind speed, but for quantities like storminess across very large areas. So that's actually counting the weather events in the model. But if the NAO, which we showed in the previous couple of slides, is predictable, and that is the source of predictability, then it may be, if there's not much else going on in Europe, for example, and it's really just coming from the predictability of the NAO, then maybe we'd be better off taking the NAO as a proxy and removing any noise that might be incurred by counting events in the model. And actually, when you do that, the panels on the right show the correlation skill again over the 20 years, and you can see that the skill is improved by doing that, particularly for temperature, where you can see now the Northern European patch, which you would expect to be skillful if you'd got reasonable predictions of the NAO, is now coming out nicely. And the patterns on the right are, of course, what you would classically expect as teleconnections to the NAO. Of course, over North America, that statement is not so true, because there the ENSO, which is obviously very skillful from November for the DJF period that we're looking at here, is obviously filling in a lot of the skill over North America. But over Europe, it looks like using the NAO itself may be the best approach. So all of those important quantities show significant levels of predictability over parts of Europe and North America. This means that we can start looking at all sorts of other impacts, and given that we have some skillful wind speed over Northwest Europe, we can start thinking about energy and transport, storms for insurance. There are various applications. We're even looking at river flows, which is what those bottom panels show. So it turns out that we can get some skillful prediction of UK river flows out of this system. So that's kind of the main result, and that's what's published in the paper we published in GRL a few months ago. But I wanted to highlight a couple of interesting questions for discussion. I'm going to skip that slide in interest of time, but just jump to this one. So if you look at the square graphic on the left, you'll see that we've plotted there the ensemble mean skill between 0 and 1, so it's the correlation score, against the number of ensemble members. So we're asking the question now, how sensitive is this 0.62 correlation to the ensemble size? It turns out that the skill rises pretty slowly with the number of ensemble members. In this case, we had 24, and the skill was 0.62. But you can see that in principle, if we had more than that, we could get up to scores maybe even as high as 0.7 or more. That's the implication here. The dotted line shows a theoretical curve published some time ago by James Murphy and co. in the Quarterly Journal, which shows just simple assumptions about what you should get given a fixed signal-to-noise ratio, and that matches very well how the skill climbs as you increase the number of ensemble members. So that's all got by subsampling the ensemble we've run. So that's great, suggests that maybe there's even more skill if we could afford to run, say, 100 members or something. But there is an interesting issue here with the speed at which that curve climbs. If we plot on the bottom right, and Aaron Kumar, who I think is involved in this teleconference, knows about this, then we see that the correlation of 0.62 is actually quite a long way above what we would expect, given the very small signal-to-noise ratio in these hindcasts. So what I'm saying here is that the signal, which is present in each ensemble member and only emerges when you average all of those members together to kill the noise, is actually pretty small given the large correlation coefficient. Now we can show that the chance of having such a high correlation coefficient with such a small signal-to-noise ratio is actually pretty small. It's less than 1 in 20, so it's 95% confident that there's a discrepancy there. And that brings us to this model, this simple toy model that I propose here, where O stands for observations, M stands for model, and if we represent the observations as S for signal plus N for noise, which might be some random Gaussian noise, and the model as the same thing, but we put a scaling factor beta in front of the signal, then we can show using Bayesian resampling, and this is work done with David Stevenson, a statistician at Exeter University in the UK, that the likelihood that that beta is 1 is very small. So it's very likely that what we're seeing, what's giving rise to the skill in these hindcasts, is just starting to emerge in this latest system. It's very, very small. You need a lot of ensemble members to hammer it out. But we're very confident that there is this discrepancy, and we're just starting to scratch the surface in terms of these predictable signals. The pattern of where the signal-to-noise ratio has these unusual values is shown in this bottom picture here from this paper by Rosie Eade from GRL 2014. And the red areas show where the discrepancy exists. You can see it's more or less the NAO centers in the North Atlantic, maybe a little bit in the North Pacific around the Kuroshio as well. So there is a particular focus on the Atlantic for this issue. Turning back, so that's one key uncertainty is this low signal-to-noise ratio. A second interesting question that might be worth discussing is where the predictability comes from. Now, when we first published the result, we identified 4 sources. In the top row here, we have ENSO composites from the forecast in the middle and the observations on the right. And this is sea level pressure between El Nino and La Nina. So you can see that there is a signal over the North Atlantic there, which would project onto the NAO. Second row down is the Atlantic Ocean heat content. Third row is the Kara sea ice, which is the sea just north of Europe. And the last one is the QBO, the quasi-biennial oscillation. So all of those low-frequency processes, which are represented in principle in a model and are very skillfully initialized and predicted, in fact, appear to be having an impact on the North Atlantic sea level pressure. But these 4 factors only explain less than half of the variance. And so we're still left explaining the rest. And so I've been looking at tropical rainfall as the classic, given all the Hoskins stuff about teleconnections to the extratropics and Rossby waves. We think that's where a lot of the skill might originate. So we've been looking at that. And if you look at this top left panel here, you can see the correlation between the December predicted rainfall and the January-February NAO. Now, the reason I've chosen those months is not to fit anything up or show you a nice result. It's because, curiously, in the hindcast, the skill is mainly coming from the January-February period. It's not in December. So the December skill is low. So we look at the December precip as a predictor of the late winter NAO, and this pattern emerges. Blue here means positive. So blue means it's wet when the NAO is positive. So you can see straight away there's a kind of El Nino signal in the tropics. And if you look at the observations on the right, although it's a little noisier, you can see a similar pattern. If you look at the actual skill of the rainfall, then unsurprisingly, the blue in the blue swathe across the tropics shows high skill in the tropics. We can then start to think about different regions in these pictures and how they might connect to the extratropics. So I've taken a few different regions. The top left panel here shows the tropical West Pacific in the model. The top right shows an observed tropical West Pacific rainfall composite. And what we're plotting here is the effect on geopotential height over the whole globe when it rains in the tropical West Pacific. So you can see those top two panels are reasonably similar. So the model is reproducing to a reasonable degree the teleconnection to West Pacific rainfall. Second one down is the Indian Ocean, perhaps also not too unreasonable. The pattern looks fairly similar. And then if we move to the tropical Atlantic, you can see that the pattern on the top two rows, in the model on the left, the observations on the right in the Atlantic sector is not so similar. In fact, it's probably projecting oppositely onto the NAO. So this is pointing to a possible problem in the tropical Atlantic in the hindcast, despite the encouraging level of skill. And then the final one is the tropical East Pacific, and again, that looks sort of similar in the model and the observations. So we find some evidence for tropical teleconnections by looking at composites or correlations with tropical rainfall. That's all quite encouraging. Furthermore, and I'm coming to the end now, we can show, I was quite surprised by this, but it turns out that the tropical rainfall is really well predicted in this system. So these four panels here show you the tropical West Pacific in the top left, the Indian Ocean in the top right, the tropical Atlantic in the bottom left, and the tropical East Pacific in the bottom right. Now the black line shows you the GPCP observed rainfall over the 20 years, and these are December means. And then the dashed line shows you the ensemble mean forecast of the rainfall. Now there's no standardization here at all. This is in millimeters per day. So the striking thing to me is that the mean values are pretty reasonable. The interannual correlation, even in the ensemble mean, is very respectable, very high, in fact, in some of these boxes, these tropical places. And so it seems to me that both the amplitude and the temporal variation of the tropical rainfall has been pretty well forecast in this system. And then if we're going to use this as an explainer of where the remaining skill is coming from in the NAO, then I've done a kind of simple thing where I've taken those four regions, those four time series, and I've just done a multiple linear regression against the forecast NAO. And I'm asking how much of the forecast NAO can we explain? And that's the bottom panel. And you can see there is a correlation of 0.74, where the forecast NAO agrees quite nicely with the multiple linear regression of the rainfall in those four regions. One little final note here is that if you see that red oval there, I've highlighted 1 year where this tropical rainfall regression did not work, 2004-5. And if I quickly flick back to the original result, you can see in the orange curve, if you look at 2004-5, you will see that that is the 1 year in the hindcast when there was a forecast bust. And there was a big discrepancy between the forecast and the observations for the NAO. So I think it's interesting that that also pops out of this tropical rainfall multiple linear regression. So I think that's interesting. It looks to me as if the NAO is partly explained by the tropical rainfall, some reasonable fraction of the variance. I couldn't swear it's 50%, but that's what's coming out of this first attempt. So that's all I had to say. So I think pretty much up to 20 minutes. I'll just quickly summarize. There is pretty good evidence here that there is skillful, it is possible to make skillful seasonal forecasts for Europe and North America. Of course, the skill is still limited, but it looks quite respectable, and it's statistically significant as far as we can see. There's much higher than we previously thought predictability of the NAO and the AO, which is very exciting. We're up to 0.6 with this system. We've actually rerun a hindcast and gone back to the beginning of the satellite period and have a higher correlation score. We're only able to run every 2 years, but we can extend it back to 1979, and we have a score closer to 0.8. So it's reproducible. We've done it 2 or 3 times now, and we've extended back to 1979. There are several sources of skill. My kind of the way I like to think about that, the analogy I have is that many things ring the NAO bell. So it could be tropical rainfall, could be Atlantic ocean conditions, could be El Nino, but a lot of things project onto the NAO. And it seems to me that that is the main pattern that is predictable that is coming out of the system. Then there's this curious paradox about the signal-to-noise ratio. We still don't understand why. We have several hypotheses and are looking into those. Why the signal-to-noise ratio is anomalously low. I guess it's kind of as if this signal is just starting to appear in this system. It wasn't there in previous systems. And the consequence for that is that at the moment we need large ensembles to hammer out the noise. You could get the maximum skill, maybe approaching maximum skill if you had maybe 100 members or so. Nevertheless, the correlation scores are still there, and that means that in principle, the risk of daily extremes, as I showed you in those surface maps, are now predictable because they are governed by the large-scale flow, as we all know, and so there is hope to make long-range forecasts for the risk of daily extremes, and that means that there is an exciting possibility of many downstream applications. I'm losing my voice, so I'm going to stop there, Dan and Ben. There are some references at the bottom of the page as well, if you want to look at the papers. Thank you.
Thank you very much, Adam. We really appreciate you willing to do this when you have a cold. So we have over 60 attendees, so we really do need to use the hand feature, raise your hand feature for questions. So I want to open the floor for questions. Does anyone have we have a couple of minutes. Does anyone have a question for Adam?
Yeah, Ben, Vasu has a question. So Vasu, I just unmuted your line. Go ahead.
Hello. It was a wonderful talk. You showed this forecast initialized on 1st November, which I gather would be a 1-month lead. Do forecasts initialized in December have similar results, or are they degraded? Or is there a reason why you saw...
So we ran 2 standard tests, one from early November and one from early May. So we run for those 2 seasons when we test new systems. That's the only reason. Now that we've been running the system in real time and we produce all the other hindcasts on the fly in real time, then there is skill through the rest of the winter season, but not in the summer. So the skill peaks in the winter as we come into autumn, and then decreases at the end of winter in sort of March, April time.
Thank you.
So, Ben, we have 2 more questions, but I'll leave it up to you in terms of whether we should move on or maybe save it for the discussion at the end.
Let's go ahead and try to do those.
Okay, great. So the first one's from Huug Vandendoel. Huug, your line is now unmuted, so go ahead.
Okay, you can hear me?
Yep, we can hear you.
This is Huug Vandendoel. Well, my question is, does it matter that you assume that the signal is the same in the model and the observations except for a magnitude factor? Or should we keep open the possibility that the signal is not exactly the same in terms of distribution and so on?
Yeah, that's quite possible, Huug. We just did this simple test.
Right.
Given that we were just looking at the NAO, I guess we were, and when we look at the ensemble mean signal and look at the pattern of that, it does look very like the NAO. There's not much in terms of at least in the hindcast, that is coming out as predictable much beyond the NAO. You're right, though, it might be different in the real world, but in this simple test, we assumed that the patterns were the same.
Mm-hmm. So does this test work if you replace the observation by one single member of the model?
So that's an interesting point. So when you do that, you get a very interesting curve. You remember can you still see my slides?
Yes.
Yes. We see them, yeah.
Yeah. So this picture here on the left, where the skill climbs as a function of ensemble size, that's where you are subsampling groups of ensemble members and correlating them with the observed evolution. If I make the same curve, but I replace the observations with any single member from the hindcast, then the curve climbs much more slowly and asymptotes at a much lower level, suggesting again that the predictable signal in the hindcast is smaller than the predictable signal in the real world. That's the only conclusion I can come to.
That's curious, yeah.
Yeah. Aaron Kumar has written about this possibility in several papers already, actually, but we're seeing that here. Yeah.
So we have time for one more very quick question.
Okay, great. So that's Siegfried Schubert. Sig, your line is unmuted now. Go ahead.
Okay, Adam, also very nice results, nice talk. I'm just wondering about the interpretation you have of this being ringing the NAO bell, whether another interpretation would just be that, that the tropical forcing is generating various responses that happen to kind of project onto the NAO, but it's not really ringing the NAO bell. I don't know if you have any ideas on that.
Yeah, I guess that's possible too. I guess, yeah, the one thing I would say is that, as I said to Hugh, the main pattern that is predictable is the NAO. It looks very similar to the NAO. But we don't see signs of, if we look at if we kind of do weather clustering, weather type clustering, for example, it's really only the NAO cluster that's significant. So you're right, they might just be hitting that somehow, but yeah, I don't know, but it's certainly true that the predictable signal looks like the NAO.
Mm-hmm. Okay, thank you.
Okay, I think we need to move on. So I guess, Dan, we need to have Tim share his desktop.
Yeah, that's right. So I just transferred control over to Tim's computer. And
okay, can you see something on my desktop now?
No, not yet. So just click the Share My Desktop button, and then we'll be able to see your screen.
Okay, that's good. And then I'm going to skip down here. Now, can you see that?
Yeah, it looks good.
Good. I can't make it anymore.
I want to thank Tim, and I'll give you a 3-minute heads up if by coming close to the end. Okay.
Okay. Thank you.
Thank you, Tim.
That's fine. So I must confess that I've not got as slick a presentation here as Adam gave, and it's been prepared a little bit at short notice. So it's basically taking some slides that I've presented earlier this year. Some of you will have seen some of these slides, and then a little bit of one new slide, and that's the one I want to talk about most. And I want to acknowledge Laura and Franco, who worked with me together on some of this material. Okay, let's see if that's going to go down. So I just want to say a few words about the seasonal forecasting system we use here at ECNWF, and then I'm going to be talking about the Northern Hemisphere winter circulation. So it's not just the NAO, but the NAO, AO, PNA. And the main point of my talk really is to discuss the challenges of sampling, because this issue of low signal to noise, it's not specific to the Met Office model. We see that as well, and I suspect it is where the state of the art is at the moment. So just a few words about our system. The atmosphere model we're using is running at a resolution of TL255. That means the Gaussian grid points are 0.7 degrees spacing. So we've got slightly fewer points, I think, than the Met Office, but it's not such a different atmosphere resolution. 91 levels, so again, it's a full stratosphere model. Perhaps the biggest difference compared to the Met Office system is that the ocean model resolution we use is much more modest. It's essentially a 1 degree global model, but then enhanced resolution at the equator, so we can do the ENSO dynamics properly. Our operational system has a 51-member ensemble, and we have 30 years of reforecasts. The standard sort of operational production just has a 15-member ensemble size, but we've extended that to the full 51-member ensemble size for 4 start dates per year, including the November start. So, like Adam, I'm basically going to focus on the winter circulation here in this talk. Yeah, you'll see as the talk goes on, and it's clear from what Adam said, a 15-member reforecast set doesn't really tell you very much about the winter circulation. So just to make the point that the overall seasonal forecast system performs very well. Certainly the ENSO forecasts are very good. We're particularly interested, of course, in what's happening over Europe. And as soon as you're in the mid-latitudes, you have to be thinking more of probabilistic scores. So these are sort of reliability diagrams where we plot. Okay, you can see my arrow here. We plot we bin things, the forecast probability, and we say, okay, if we predict there's a 60% chance of something happening, this is being above the upper tercile, then what fraction of times has it actually happened? We'd like it to be 60%, we'd like things to be on this diagonal line. It's not bad if you look at 15 members, this is for temperature and summer in Europe, but if you go to 51 members, you really get things a little bit more on the diagonal, and the various scores, reliability score goes up and the ROC scores go up as well. If you look in the winter, things do not look so good over Europe, and when you look at just 15 members, you see this looks fairly flat. In other words, the model might predict warm or cold temperatures with various probabilities, but what the model says doesn't make much difference, except maybe a few points up here. The size of the circle is how many times this happens in the bin, so there's very rare occasions up here. So 15 members, it's really not looking good at all for Europe in winter temperatures. If you increase the ensemble size, the picture actually does change rather, and it's still not as good as in the summer, but we clearly do now have some ROC skill score, and the reliability is substantially better. And it basically comes down to the fact that the system is very noisy, and if you only have a small ensemble size, you're basically still looking at noise. And particularly when you're trying to count the number in a tercile category, where so null hypothesis would be 5 in each category. It's just so noisy that here you really can't do that, and you have to have a bigger ensemble size to calculate these sort of probabilistic scores with any reliability. Okay, so because I sort of just grabbed these slides from talks I've given earlier this year, then there's a few slides now on the Arctic oscillation in particular. I'll sort of skip through this, and many of you, or most of you, will have seen the results that we have with our system 4. That in our system, it's really the Arctic oscillation skill that comes out rather high. We have a 30-year correlation of around 0.6, and the sort of time series looks like. And I want to be quite explicit. Here we have scaled the amplitude of the ensemble mean in system 4 by a factor of 6, so that it's then comparable to the observed amplitude of the anomalies. And this high correlation is surprising because, as Adam says, the model is noisy. The models are noisy. Our model, Arctic oscillation, is very noisy. It struck me as well. It's not the sort of thing you're supposed to do in statistics, but I do notice that the sort of about the biggest bust in the system is Pinatubo, and we know that volcanic aerosol can affect the winter circulation pattern, and we don't represent that very well in our model. And after El Chichon also is not so good. If we take out the volcano years, the correlation happens to be higher, but I think you should not take that as a sensible number, because statistically you're not allowed to do that sort of thing. If we then go and do a proper or a detailed statistical analysis of what's going on with those time series, there's a few things I want to point out. Firstly, that if we look at the actual variability in the model, the ratio of the standard, so we basically calculate the standard, we treat all of the individual model ensemble members as realizations of the truth, and from that we can calculate what the standard deviation of the intriennial variability of the seasonal mean Arctic oscillation is. And we have that's very well sampled from the model. From the observations, we just have the 30 years of data, so that's slightly less well sampled. We look at the ratio, and it's close to 1. And we can do some statistics, calculate the confidence interval on that. And the bottom line is the model variability is consistent with observations. So if we're looking at the actual variability of the Arctic oscillation model, we can't see anything obviously wrong with it. The signal-to-noise ratio comes out about 0.1 in this data set, although the sampling uncertainty on that is is not quite negligible, but it's certainly it's below 0.2 anyway. So the signal is very weak in this system. The anomaly correlation that we get is, as I say, about 0.6, just above 0.6. We can then do some basic bootstrapping to establish some confidence intervals. And firstly, we can bootstrap over the ensemble size, which basically says if we repeated this experiment with the same years, but we just ran a different set of ensemble members, or maybe we extended the ensemble size up to a really big number, 1,000 or 100,000 or something, what would we converge to? The central estimate is 0.7, so just as an Adams curve, in a noisy system, if you have a limited ensemble size, you're probably going to underestimate the skill. However, it's worth pointing out that the confidence interval covers a much wider range, and here is for a 95% interval 0.55 up to 0.81, and so we might think we might expect to get a bigger correlation score with a bigger ensemble size, but actually if we increase ensemble size, it's possible that the skill will go down. We can't rule that out. It's certainly possible. And the other thing to bear in mind is that this is basically increasing the ensemble size towards infinity for this set of years. A completely separate question is if we were to run the system for the next 30 years or a 300-year period, what would we end up with in the longer term? And here the range, the uncertainty range is actually quite a lot larger because 30 years just is not a sufficiently long period to tie down. And you saw from the time series I showed and the time series Adam showed, you can maybe have a few big points that can dominate, and either you get a high correlation or low correlation, but it's just not a very big sample to assess that. And the key thing from the statistic here is we can then ask the question, how consistent is this anomaly correlation skill with the signal-to-noise ratio? And basically we can do some statistical modeling, and for our system and for this set of data, there's only a 0.0004 chance of getting this level of correlation with a system that has this signal-to-noise ratio. So for our model, which may be signal-to-noise ratio, our signal-to-noise ratio is a little bit lower than Adams. In our case, there's no way at all we could be getting these anomaly correlation values if the signal-to-noise ratio was representative of the real world. So we're confident the model is too noisy. That just says it. We can look at other regions, other teleconnection patterns. So for this 30-year period, our PNA comes out around 0.7, but the signal-to-noise ratio is around 0.64, and so that is maybe fractionally better than we might expect, but it's perfectly feasible. So that the p-value associated with that is around 6%. And for the NAO, for this 30-year period, and we use UF definitions of these based on Z500, projecting the observed patterns onto the model onto the observed patterns, anomaly correlation comes out around 0.46, 0.47. But again, in our system, the signal-to-noise ratio for the NAO is very low, as it is for the AO, and therefore this level of skill is too high. It's much higher than we expect because the NAO has got low predictability, but we have moderate skill. So the NAO and the AO are showing similar behavior. We're getting much higher skill than we should be, given the signal-to-noise ratio in the model. One question that we have been able to look at is the question of resolution, horizontal resolution. This is work that's been done as part of Project Minerva, and ECMWF has been involved in this together with colleagues in the US. And the ECMWF seasonal forecast model has been run at different atmospheric resolutions. This is not quite the same cycle of the model that we use for System 4. It's a slightly more recent version. We've got 30 years of winter reforecasts. We've got 51 member ensembles for those 30 years, and we've got this at T319, and we've got it at T639. And when we look at compare the behavior of those two systems, very many things look very similar in terms of the model climate and biases and patterns and so on. The PNA has got a very similar level of skill, around 0.7. Signal-to-noise ratio is very similar. When we look at the AO, again, things are fairly similar between the resolutions. The NAO, the signal-to-noise ratio is very similar, but the actual skill, the anomaly correlation, is actually much higher with the 2639. And this is the one thing that seems to be really substantially different as a function of the high resolution. So, and that comes out, you can do some significance testing that is significant in this data set at a 5% level. So on the one hand, that's sort of encouraging that perhaps the structure of the NAO, which is not so well represented in this model, or at least it doesn't quite get the forecast skill right, this really does seem to improve with the high resolutions. That's encouraging. On the other hand, this signal-to-noise ratio problem, which we somehow consider to be a very fundamental problem, this does not seem to get better. So I don't know, maybe that was even a little disappointing that the signal-to-noise ratio was not sensitive there. So this is the slide that I suspect none of you have seen, or very few. I sort of prepared it in June of this year. And it's really just a slide to illustrate the challenge of these sampling errors. You saw earlier on I showed some of the actual calculations of numbers and confidence intervals and stuff, and this is basically the same in graphical form. It's looking just at our own system 4 winter forecasts, and we're looking at the NAO here, the AO in the middle, and the PNA. And for each of these regions, we're looking at the correlation score, and the black line here is just the calculated value over the 30-year period. And the black line is for a 14-year period, and the red line is for a 30-year period, the full 30-year period. And we then have some confidence intervals, and the boxes show the uncertainty over ensemble size. In other words, it's saying, maybe I do this red one first here, that okay, we have a 30-year period for the NAO. We calculate around 0.44 or something for the anomaly correlation, but actually, if we were to run if we were just to increase the ensemble size, we're fairly confident we'd be somewhere in this range, but we don't really know where in this range we would be. So that's quite a wide range of values, quite a significant uncertainty for a 51-member ensemble. And then the whiskers give the range that we expect bootstrapping over the years. In other words, if you say, we're not really interested in the skill for this particular 30-year period, we want to know what is the overall skill that we expect in the long run, then it's a bigger range. And if we look, instead of at a 30-year period, we look at a 14-year period, then of course the sample sizes the sample is smaller, the ensemble size is the same, but still the uncertainty's got bigger, and the uncertainty in terms of the long-term skill is now we really can say almost nothing about it. So these are the values for the NAO, the AO, and the PNA. One of the vexing conclusions of this is about comparing models and comparing model versions. And of course, sometimes there's interest in comparing scores between centers, but we're also very interested in comparing scores between an old model version and a new model version. We want to know, is the new model better? And the problem we have is that if we run over 30 years and we run a 50-member ensemble, the uncertainty in the skill is rather large. And in fact, any improvements are likely to lie within the uncertainty range of the scores we calculate, even for this given set of 30 years. So this just means that it's a very big problem to try and do model development or to compare new model versions with old model versions, because these sampling errors are so large with the level of noise we presently have in the system. Another way of illustrating that is just shown here. This is an experiment I did a year or two ago, a year and a half ago, and the only panel I want you to look at really is on the right-hand side, which is where we look at the signal-to-noise ratio. This is the signal in the ensemble mean. versus the noise in the ensemble mean. So in other words, you know, is the ensemble mean itself just badly affected by noise or not? And the green areas here are less than 1, the white areas are 1.5, and this is with a 100-member ensemble. So a 100-member ensemble, the sort of orange-red areas, this is signal-to-noise ratio of 2 or 3. So here we can run a 30-year period, this is a 30-year period, and we can have some idea of what the ensemble mean is doing. But over in Eurasia, we don't really know so well what the ensemble mean is doing, even with 100 members ensemble. So this noise problem is really severe. So to conclude, okay, at ECMWF, our system seems to have substantial skill in predicting the AO phase over this 30-year period. How typical this is of long-term performance or future performance is not so well known. There's quite a big error bars on that. And the key thing is that the model signal we think is too weak and the model is too noisy. Another point bearing in mind is the scores themselves, anomaly correlation scores, are rather unstable. In particular, they can be very sensitive to the choice of years, especially for shorter periods. It's not too bad if you're comparing two models for the same period, but the actual numbers themselves can really jump up and down depending which years you have in there. It's also sort of interesting that the relative skill of AO versus NAO can vary a bit between different model versions we look at. Sometimes it's the AO where the skill is highest, which is true of our operational system 4. Other experiments we do, the AO scores go down and the NAO scores go up. So it's not terribly stable there. Higher resolution, we've gone as far as T639. It does appear to help the NAO in particular, quite a big improvement. Doesn't help the signal-to-noise ratios. The caveat is that's essentially a single experiment with a single model version. So ensemble sizes were reasonable, but you know, quite how general that is, you never quite know. And then somehow the main conclusions really I want to draw out are about sampling. Sampling over a number of years. This is always going to be, it's an obvious problem for systems that don't have a high signal-to-noise ratio. So for something like ENSO, where the signal-to-noise ratio is, it's not huge actually for ENSO, but it's moderate, we can do some reasonably sampling over a few decades, but this is always going to be a problem in the mid-latitudes. In principle, we need as many years as possible, but there are limits. You know, we can't get 500 years of observational data to study this. And the question of how far back we can go, we probably need to understand the sources of skill to know that. You know, can we go back to the beginning of the satellite era? Could we go back to circa 1960? If it's sort of ENSO and SST that basically drives everything, maybe we have some knowledge of SSTs for the whole of the 20th century that we could study this. So we perhaps need to understand those sources of skill to really see how far we can push this. Another problem I think that we run up against is that the ensemble size that we often use is just too small. You know, we often do experiments with ensemble sizes, let's say of order 10, maybe 10, 20. But given how noisy our models are at the moment, we should probably be doing experiments. And I hadn't seen Adam's slide, but you know, ensembles of order 100 is what I think is what's necessary to get clean results until we can figure out, you know, how we can get our models perhaps having a slightly more realistic level of signal in them. And of course, the consequence of this is for costs, because we've mentioned, you know, we've got evidence that high resolution really helps, particularly the NAO. That's the experience of the Met Office. So if we need really high resolution models, we need large ensemble sizes, we want to have lots of start dates, and if we're then going to want to do lots of experiments to improve our models, the costs are a very significant issue. So that's it. Thank you.
Thank you, Tim. That was great. And we have a few moments for a couple of questions for Tim before, I know he has a family obligation, so he does have to leave right on time. So are there any questions for Tim?
Yeah, Hoog just raised his hand. So Hoog, you're unmuted. Go ahead.
Okay, you can hear me?
Yes, we can.
Okay, so I noticed the in brackets EOF behind NAO and PNA. So I guess my question is, does it mean that they're not really those teleconnection patterns, but the EOFs that look a lot like it? And associated with that, in the S2S conference, I thought that this all applied to clusters that had been calculated, not those EOFs. So has this sentiment changed a little bit during this calendar year?
No, this is exactly as done before. This is how we do it for the Arctic Oscillation. We use essentially exactly the same method as CPC, and the difference is that we use the era interim reanalysis as the basis of calculating the observed patterns, and then we project that in the model onto the observations. That's done for sea level pressure, mean sea level pressure for the Arctic Oscillation, and we use Z500 restricted to sectors for the NAO and the PNA, which is how we've done it actually operationally for quite a large number of years now. We've produced these like that since System 3, I think.
Okay, any other questions?
Well, Ben, that's it in the list. So, if anybody else has a question, use the raised hand feature. Otherwise, Ben or Arun, Adam, Matt, if you have any questions, you're unmuted.
So I guess I have a question for both Adam and Tim. I didn't really hear an answer to this signal-to-noise issue, why these correlations are so much higher than the signal-to-noise issue. So is there a feeling, do you have an idea of why these correlations are so much higher than one would expect?
Do you want to go first, Adam?
Answer first, Tim, or do you want me to go?
Well, I've got
why
a few
don't we start
ideas.
with Adam and then Tim? I mean, I'm just perplexed
Okay,
by
I
this.
mean, we don't, the short answer is we don't know, Ben. I think it's a really hot topic. It is, for my group, the top question, research-wise now. So we have a number of hypotheses, but to be frank, we don't yet know.
Okay, Tim?
Yeah, well, that's sort of a little bit my thinking. I can throw in a few ideas. So I guess motivated by the fact that, we started off looking more at the AO, because in our model that was the index that had the highest skill. Been looking quite a bit at, or I've been looking at the sort of downward connections from the stratosphere to the troposphere. And in the stratosphere, we also can get good skill in the AO, but or the northern annular mode, if we call it that, higher up. And to my mind, it is, if we have and the signal to noise ratios are higher in the stratosphere, and certainly at the beginning of the winter. And so one hypothesis is that there is signal up there, that in the real world it finds its way down, and in the model that the downward coupling is just too weak. And this would be a sort of, in rough terms, an explanation of why you could get the sort of the right signal, but the amplitude being too weak. But we've looked at the correlation between the surface AO and the annular mode higher up, just sort of month-to-month fluctuations. And in the model, this actually matches the observed correlation. So it's not that they're disconnected in our model and connected in the real world. I think it's more a question of, in the model, the influence is basically going upwards. And so we're getting a lot of noise, if you like, or unpredictable behavior in the troposphere that's then putting noise up into the stratosphere. And in the real world, I'm sure that happens, but we're also getting, one hypothesis is we're getting some signal coming down from the stratosphere, and the model is not picking that up. But how that happens, observational studies and whatever, from the literature I've read, is just not understood. And I worry about all sorts of things, but there's questions of model numerics, there's questions of resolution, there's questions of vertical resolution, there's questions of vertical diffusion in the models. maybe even radiative processes, and the level of humidity we have in the lower stratosphere and the tropopause. So there's all sorts of things that are not quite perfect in the models when you start to dig into it. But which of them is likely to actually give a substantial change, that is harder to see, actually.
Okay. It's a great problem. Terrific. I can see that now it's noon, and I really do want to let Adam and Tim go, and for Adam to take care of his cold and Tim to take care of his family needs. So again, I really want to thank both of you for excellent presentations and contributing to the Climate Prediction Task Force. This was really just terrific. I really appreciate it. And unless there's any other announcements, Dan, that you need to be made, I think we can end the call here.
Yeah, I would just echo the thanks. Very, very much appreciate Tim and Adam taking the time to present.
Yeah. So go ahead.
It's been a pleasure.
Thank you very much
for the invitation.
Yeah, thank you very much, Adam. This has been great.
Okay, cheers. Bye
Cheers.
now.
Bye-bye, all.
Take care. Thanks, everyone.
Yep, bye.